welcome back to another episode of Planet Hunters Coffee Chat. I'm your host, Cassie Prolongo, and of course, joining me as always, the lovely Nora Eisner. Good to see you, Nora.
Good to see you too. It's been so long.
It has been way too long. Oh my gosh. We were off air, so to speak, for a while. Do you want to tell them why we were off air, Nora?
Yes, I had a bit of a busy couple of months. I was just finishing my thesis, so I handed in a couple of weeks ago. So glad it's done. And yeah, so I was just busy doing that. So I had to write 250 pages about everything I've done in the last 3 years. And I did it, I submitted it, and now I have a couple of weeks to rest until I have to prepare for my defense. So I still have to orally defend all the work I've done. So fingers crossed.
Yeah, congratulations. Well done. Super proud of you. And it's going to be awesome calling you Dr. Eisner pretty soon as well. That's going to be a lot of fun.
Yeah, it hasn't quite sunk in yet. We'll see. Maybe once I actually am doctor, I'll sink in that that's what's happening.
Yeah, it's going to be great. So we're really excited, and yeah, so it's for a good reason. We promise. We've had a lovely couple of people who actually reached out to us to ask if what's going on. Are we coming back? And we are back. So we are filming a couple of exciting episodes over the next few weeks, and then we might have another break depending on what happens with Nora's defense, as she just mentioned. But other than that, yeah, things are going well. So thank you for joining us today. I hope you have your coffee or tea or beverage of your choice. I have my lovely funny coffee mug today that was given this to me from Katrina, who's our social media person. It says "Go on yourself" in Scottish, I'm assuming. So yeah, she's absolutely lovely. And but yeah, it says definition: a shout of encouragement. Go on yourself. Go on yourself.
Can be our motto for today. I think that's great.
Go on yourself. Yeah, it's like she said, it's like the definition, it's like an American saying, "You go girl," kind of thing.
I'm like, okay, love it.
Love it. Very cool.
On yourself.
Yeah, exactly. So anyway, sorry, we're goofy today. It's been a while since we've seen each other. So Nora, what are we diving into today? Since it's been a little bit of time between our last episode and today.
So today we're going to look at something we've talked about a couple of times, has come up quite a few times actually, which is radial velocity observation.
Oh, yes.
So this is how radial velocity observations is another technique used to discover exoplanets. It was actually how the first ever exoplanet was discovered. Pegasus 51b was found with this radial velocity observation or method. But it's now become more commonly used to observe planets that are already known. So already, if you found a planet using the transit method, then often it is observed using the radial velocity method because it can be used to determine its mass. And the reason why determining the mass of a planet is so important is because if you have the radius of the planet, so kind of how big it is, and you have how heavy it is, then you can determine roughly how dense it is. And this density can give you an insight into what it's made of, whether it's a rocky planet or whether it's a gas planet, which is exciting because if we're looking at these planets, that's something we want to know. Yeah. And the mass can also help you determine whether it has a large atmosphere, and just give you much more information than we would otherwise have just from observing the transits and from having the radius of the planet from that method. So we mentioned the radial velocity method, like I said, in quite a few episodes. I think the last time we mentioned it, this could be wrong, but I think the last time we mentioned it is when we talked about the triple star system. Yeah. So yeah, is that right? I think so too. Yeah, I think we talked about it then. So that just shows the radial velocity method is useful to look at both planets, but also to look at stars. So I think we should briefly go over what it is, and then we'll look at some code and we'll look at some data afterwards. How does that sound?
That sounds great. Let's dive into it. And I'm pretty sure we've had some comments about this on our YouTube as well. So hope that you guys get a lot out of it. So let's dive into it, Nora. That sounds great.
Cool. Okay, yeah, so the radial velocity method is, if you imagine a planet's orbit around stars, they do a nice circle around these stars. What's probably slightly less well known is that the stars also orbit around the planets. So they also orbit, well, they both orbit around a common center of mass, around a common point, which is very close to the star. So the planet does a big circle and the star does a tiny, tiny little wobble on its orbit. And it's also a tiny little circle. But because that star is also wobbling, caused by the gravity of the planet that's going around it, that means that that star is sometimes moving towards you and it's sometimes moving away from you because it's moving in that small circle, very, very tiny. So if we're looking at the light of the star, that light is sometimes kind of, as the planet is moving to, as the star is moving towards you, that light is more squished together, so it appears more blue. And if the star is moving away from you, that light is stretched out and appears more red.
Right.
So this is called the Doppler effect. If we measure the light, we can see it sometimes a bit more red, sometimes a little bit more blue. It's analogous to, you can have this with sound as well. So sound is also waves. And if you hear, for example, I don't know, an ambulance moving from, you might have heard this already. If you have an ambulance moving past you, the sound will change from if it's moving towards you or away from you. Cassie, why don't you give us a little illustration of what that would sound like?
Wee, 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 wee.
That was great.
Off the cuff. Woo! I'm sorry.
That was good.
This is why you keep me around, Nora. Oh my God.
The sound effects.
Yes, but you hear it all the time. Police sirens, fire engines, or an ambulance. Yeah, exactly. And you're like, oh gosh, you can hear it coming, and then when it's there, and then when it goes away. So the same kind of effect. So that's the Doppler effect for sound, as you mentioned.
Yeah, exactly. So we're just looking for this Doppler effect, not in sound, but in light. So the way we do this is if we take the light from a star, light is made up not just of one wavelength, it's made up of lots of different parts. So if you think of light passing through a prism, you might have seen that, or light reflecting off a CD, you also see a pretty little rainbow, because that light is being split into all of its different parts, all the colors of the rainbow. So if we do this to the light of the star, we can spread it all out. We see all of the different colors, and there'll be certain parts that are dark. So there'll be certain parts that have parts of the light of this, it's called a spectrum, certain parts of the spectrum that have been blocked out. So it's been blocked out because the light is passing through the atmosphere of the star, which is causing these, we call them absorption lines. So where the light has been absorbed by the atmosphere. So if we can take these, we'll see an example of this in just a moment. We'll show a spectrum. We can measure the location of these lines really, really carefully. And those lines will shift either towards the red side or towards the blue side, depending on whether that star is moving towards you or away from you. So by measuring this very precise location of these darker lines, we can see the wobble of the star, which is induced by the planet going around it. So that can tell us about the existence of a planet there, or it can tell us about how big that planet is. So if you have a large planet that's close to the star, you have a really big wobble of the star. And if you have a small planet that's far away, you have a much smaller wobble of that star. So knowing those properties can tell you about what planet we have and what its properties are.
Slight sidebar, will the James Webb Telescope be able to measure things like this a little bit more succinctly or more efficiently, or the
James Webb can definitely do this. It's got a spectrograph on board. What the James Webb will be really good at is doing, also taking these spectra, so also taking the light and splitting up into lots of different parts. And then instead of doing this over time to kind of get the wobble, doing this as the planet passes in front of the star. And if the planet is passing in front of the star, then part of that light from the star will pass through the atmosphere of that planet, which means we can kind of determine which lines are dark. So these absorption lines tell us what's in the atmosphere. So this can tell us about what's in the atmosphere of these planets. And these tools on JWST will be really good for that. So that's really exciting.
That is really exciting. We'll be able to know if these are potential habitable planets or not, maybe, depending on its atmosphere or rocky planet.
Yeah. a lot of different things go into habitable zones.
Yeah.
But they might be able to tell us whether there's water in the atmosphere or whatever else is in the atmosphere.
Yeah. Sorry for the sidebar. Thank you very much for answering my question. Excellent. Okay, so let's look at these absorption lines that you mentioned as well.
Yes. Okay. I'll share my screen.
Oh my gosh, I'm drinking cold brew today, and let me tell you, that is the best thing to have on a Monday morning.
Cold brew. It's in a tea mug, but I'm actually drinking water today. I'm cheating.
You are, it's okay. It's okay. We won't judge you.
I had a lot of coffee when I was writing my thesis, so I'm trying to tone it down.
Smart. Come down from the caffeine high. Okay, gosh. All right, so this is cool. So we've got a new notebook. I'm sure everyone will be really excited about this.
Yeah, so I prepared a notebook. I won't code live. I did this right at the beginning and I haven't done it since because I made so many typos that actually I decided to stay clear. But we could go back to that. Anyway, so radial velocity data is taken by lots of different telescopes from all over the world. Most of the time, the data isn't publicly available, but there are certain data sets that are publicly available. So we'll be using one of those data sets today. And the place where we can get those before we even go into what the data is on the ESO archive. So the European Southern Observatory Archive. We have previously mentioned this, I think. Oops, we'll just Google ESO archive. That's it. This is why I don't type live anymore. That's a good example.
It's like me when I'm trying to back into a parking space and I see people staring at me and I go over the lines when I back into a park because it's anyway, sorry. The same kind of thing. Don't look while I'm backing into a parking space. Anyway, sorry, second sidebar for today. Back to ESO, the Science Archive Facility.
Yes, so I'm going to double check which target we were looking at before. Prepared one with this target, so might as well go with this one. So the ESO archive is really, really cool. It has lots of information on it, but it is the European Southern Observatory, so all of their telescopes are in the south. So if you're looking at a northern target, there's no point looking on the ESO archive because it won't.
Right. Good to know.
You can still look, but it probably won't be in there. Cool. So you can take a tick ID, you can put it into the ESO archive, press enter, and then it will tell you what data is available. And the data we're interested in for the radial velocity observations are the spectrums. The spectra.
Beautiful website. This is a cool website.
Yeah, really well done.
Mm-hmm.
And then you have this whole list. HARPS is always great. If you see HARPS, then you should go for those. You can then download them by clicking in the top right-hand corner on the download button.
What does HARPS stand for? Sorry, did I miss that?
Oh, sorry. HARPS is an instrument on a telescope, so it's on a 3.6 meter telescope, and it stands for... Question.
It's an instrument on a telescope. That's as far as you need to know, Cassie. Thank you and good night.
I should know this, and I do know it. It's not coming to me, but I will.
Okay, you've got thesis brain still.
I'm pretty sure the P stands for planet.
Yeah,
planet spectrograph, high resolution something. Whatever. It's a tool used to take spectra of stars, and it's very good for finding planets. That's all we need to know right now.
That's
anyway, then you can go to a specific star, look if there's any data, and you can download it using the download dataset button in the top right-hand corner. And I also want to mention that if you do go onto that button, you press on the one that says data, and then you get taken to this other page, and you want to download the ancillary data as well. So you just check that and then do download zip file.
Okay.
So yeah, if you want to use data, you download it, store it on your computer, and we'll go back to the notebook to see what we do with it then. Okay, so we're going to look at just a random target. This is a target, this is a known planet that has been published. I think it was found in test data. We're just downloading it here. We can see that there's some nice transits in here. I think it's a hot Jupiter. So it's a large planet close to its host star, so with a short orbital period. So these have larger radial velocity amplitudes. So these have larger signals, larger red and blue shifts, so they're easier to see in the RVs, which is why we're using it as an example today. Cool, so you have to download the data and store it somewhere on your computer. And you can see I have a very messy computer, so I have a really long path to where that data now is. So you have to change all of this to where you've stored the file on your computer for this code to run if you're running it at home.
Okay.
So yeah,
if you put it on your desktop or something, just make sure that it's got like the desktop and everything on there. Okay, got it.
Exactly. So for you, this might be users, Cassie, desktop. Then you've got it in a folder called test files or something along those lines, and then keep that star there. That star says, look at all of the files in this folder that end in fits, and it will then give you a nice list of all those files. Okay.
Okay, that sounds good. Moving on.
Cool. So what this now is, if we quickly just show this, if we insert a cell there, it's just a list of all of those files in there. So we can get rid of that again. We don't care about that list. All we need to know is that it is in there. Okay, so we can make that a bit bigger. So what we're now doing is we're going to plot the data. We want to see what this data looks like. So we're opening this file using something called pf.open. pf is just a module that we've imported already right at the top here, which can be used to open this type of file. I should note we're using something called FITS files. FITS files are can be quite confusing and tricky to use. What they essentially are is they are a file, they're a data file that have both data in it and information. So it has a lot of, it will have a column with the, well, it will just have part of that file will just be all of the data, and part of that file will be information like who took the data, when was it taken, how long was that exposure time. There's a lot of other information in there that we also want to extract, but just to keep that in mind. But we'll go through how to use it.
Okay.
Okay, so we're just going to open one of these files. We're just taking the first one here, and we're going to plot it. And we're only going to show parts of it because okay.
Excellent. So when you plot it in at the beginning there, this will all happen automatically, right? There's no other things that you've put in that the citizen scientists have to also do, right? Okay, good.
No, they can just change the path and then download some data to change the path, and then this should all just work.
Okay, cool.
Okay, so this is an example of some of the data. So what this is showing is it's showing you have the wavelength at the bottom and you have the intensity at the top. So you can see that this has a lot of different absorption lines. If there were no absorption lines, if this was just light, just pure light that hasn't had any interference with it, any atmosphere in the way, then all of this would just be a straight line up here. But here we are seeing lots of different absorption lines. And what we can see with this spectra in particular, sorry, I keep saying spectrum. With this spectrum, spectra is plural, spectrum is singular. I get it wrong every single time, just bear with me. We can see these lines, these dips that we're seeing, these lines, they're really clear, and they are, they're quite narrow. So this is a really good start to look at. We've got high, what we say, signal to noise. We have a lot of signal and not very much noise, not very much scatter. So this is a good start to do radial velocities with. If you can imagine, if you have these lines smeared out, then it'll be a lot harder to measure their exact location. And we really need their exact location because the stars wobble on such small scales that those exact locations really make a difference.
Okay, so this is not one that you could be off by a little bit and have the same thing. It could actually determine whether or not, okay, got it.
Yes. This needs to be very, very precise. Okay. Cool. So that was just an example to show what one of these spectrum look like. Mm-hmm. Spectrum. I'm now confused which one's plural and which one. Anyway, it doesn't matter.
See, doctors, they're just like us. I love it.
I'm not a doctor yet.
You might as well be at this point.
Cool. So we're now going to look at, so remember how I said we have to download both types of, we have to download the data and the ancillary data. So now we're going to use the ancillary data, which is also in that file that you've downloaded. And we want to use files that end in G2A fits.
Okay.
And the reason why we want to use those files is because those files have the radial velocity measurements already extracted. So those have those measurements extracted where it's telling us whether it's shifting slightly in one direction or slightly in the other direction compared to where we expect those lines to be.
Right.
Sorry, so what I didn't say actually before is that all these lines, all these absorption lines, also, if the object isn't moving, are expected to happen at a certain wavelength. We always expect, so we expect these to always look the same if the object isn't moving. So we can compare these to templates of what we expect the rest wavelength, the non-moving object wavelength to be, and that's how we get these radial velocities.
Oh my gosh.
Sorry,
that's a
lot of information.
it's kind of intense, because if you look at like those lines, so when you just look at, can you go back up to the graph up above? Can you tell by looking at that and where the wavelengths are, like, can you determine whether or not there's an atmosphere? Or you said this is a hot Jupiter. Like, what can you determine from this just looking at the graph? Exactly. Maybe go over that once more.
So this doesn't tell us anything about the planet. So we're not doing transmission spectroscopy. So transmission spectroscopy is where we look at the light passing through the star. What we're doing here is this is only the light from the star. This is what we're just looking at. So this can tell us about what kind of star it is. Different types of stars have different absorption lines. So these lines will look different depending on how old the star is, how hot the star is, and all these other things. So this can tell us about what type of star it is, but this doesn't tell us anything about the planet yet.
The planet. Okay, got it. All right.
Good thing to clarify though. Okay, so remember when I said that these FITS files are very complicated and they have both data and they have lots of information? Here is an example of the lots of information. We are now opening one of these other files, and we're printing, it's called the header, where all this other information is stored. And you can see this is just an absolutely endless list of just lots and lots of information that we don't really need to worry about. I'm going to make this small again. Ooh, just fast. Okay, gonna make that collapsed again. The only two things we really care about for now are the time, which we can access using this command, this line of code here. And we want to know what the radial velocity observation is. So this is the CCF RVC, is just what it's called. Okay.
That's the code to put in.
Yes, I should also mention, sorry, I should have actually said this before. So depending on what instrument the data comes from, even if it's from ESO, there are lots of different instruments in the ESO archive. These commands will be slightly different. So I'm giving you the code to work with HARPS data and not with any other instrument. But if you have questions about other instruments that you found data for and you want to use, you can put a note in the chat and we'll have a look at it.
Cool. Sidebar to remember.
Yes, yeah, keep that in mind. Okay, so we're going to open each file in turn and store this information of the time and the radial velocity measurement as a list. We want to have all this information together so that we can plot it, because plotting is always useful. It allows us to determine properties. So that's what we're doing here. We are creating two empty lists. We are then looping through the file. So I'm saying for each file in turn, open it and tell me what the time and the radial velocity measurement is. That's down here. And then just add it to that list. Add it to this, what was an empty list at the start, and at the end will be a full list. And then we have those two lists, so we can plot them. And you can see this is just, looks quite messy. This is just the radial velocity in meters per second. So it's how quickly it's moving, in what direction, versus the time. And this is, I would say, impossible to see whether there is a trend in that. So we'll scroll down. This was similar to when we looked at the test data. Often it was more difficult to see what was going on when you just looked at the raw data and you actually wanted to phase fold. So this is what we're going to do now. We already know the period because we saw the test light curve all the way at the start here. So we can extract the period from that. So we're going to do that. And we've got the period, we've got the time, we're going to phase fold it, and then we're going to plot it.
And quickly though, if you have any questions about that, and if you're like, I don't know what she's talking about with phase folding, we have other episodes where Nora goes into it. Look at those, or some of our earlier episodes as well.
Yes, and phase folding with RV data, radial velocity data, is exactly the same as phase folding with transit data. It's just chopping things up and folding them on top of each other. Cool. I have like this hand motion I do whenever I show phase folding.
Like this, chopping? Like this. I like it.
Soon it'll just, I don't even need to say it anymore. I can just mark it out.
Do that. Sounds
okay.
good.
So this is the phase folded data. So we can hopefully see that we're starting to see a slight curve. There is one data point all the way up here. We're not going to worry about that, but we're seeing a curve, and you can see that sometimes this velocity, the motion of it, the speed of this object, of this star, is positive. So it's moving away from us, and sometimes it's negative, so it's moving towards us. So we can see it periodically goes from moving towards us to moving away from us, and that's because of this large planet moving around it.
Yeah.
So to see this even more clearly, we can create a model for it. This is a very simple model. You don't need to worry about the function itself. You just need to know that there is a function, this thing that you're seeing here. We have some parameters. You can usually, if it's a published system, you can get these from the publication. So the eccentricity, we'll just set to 0. Omega, we can also just set to 0. Inclination, if we have a transiting planet, then we know that the inclination has to be close to or exactly 90 degrees, because that's the inclination between, this is the star and we're over here, the observer, and this is the planet. 90 degrees means it's passing between us and the observer. So we know if we are seeing this transit, it has to be 90 or close to 90 degrees.
And this one is 86, so that's pretty close, basically, so that we know that we're on the right track for it. Okay.
Exactly. And K, this is the really important one. This is the amplitude of it, so how large that signal is. So that will then, the amplitude is what we fit for, is what we make the model with, but that will at the end tell us how massive, how heavy this planet is, which is the information we want from this. So we can do that here. I've put in the values, which I know are correct from the paper that has been published.
Okay, I was just going to ask, so once more, you got all those values from the paper that was published and you plotted those in. So if people wanted to do this for anything else, they would need to get it from the paper as well.
Yeah, get it for the paper is the easiest way of doing this.
Okay.
Or play around with the parameters and see what you get.
Yeah.
But, which is a fun thing to do.
Yeah.
Okay, cool. So we have plotted a line through it, and we're starting to see that trend that we saw in the phase folded model, but we can also phase fold that model, and here we have that line fit to the data.
And the outlier we just ignore because that one is just whatever, the one that's okay.
Yeah, I'm going to assume that something went wrong with the radial velocity extraction. So this would be another case where you dig more into that giant header with lots and lots of information on it. Maybe there was a cloud in the way. Maybe it was just taken at not favorable conditions. There can be a number of reasons to why that point is wrong. Maybe that point is correct and it actually deserves further investigation, but for the sake of today, I don't think we don't need to look into that. Okay. We can assume that it's an outlier.
Cool. Excellent.
Okay, so given this, this is the last thing we'll do, given this amplitude that we have, given how large this signal is, we can now determine how heavy this planet is, or how massive this planet is. So we can do that here. It's with this function called determine det _ mass, so determine the mass of the planet. In order to determine the mass of the planet, we do need to know the mass of the star. And we can get that information from, from exofop. So we can go onto, we love exofop, we use it for everything.
I love it. Exofop's a great website.
Yeah, so we can get that value from exofop. For this case, it's 0.92. We just determine that here, and then we can run this function, and that can tell us that this mass has an approximate, this planet has an approximate mass of 16.6 times the mass of the Earth, which is exciting.
Yeah. Very exciting. Gosh, okay, so there was a lot going on here, but you're going to upload the notebook so that people can follow it. Okay, cool. So going back through here, because it was, I'm going to have to go back and review this, to be honest with you as well. What are some of the main summary points that you want people to be aware of, just so that while they're going through it? Downloading the stuff from the ESO Archive Science portal, ticking that second box where they get the ancillary information.
Yep.
Make sure it's the HARP star. Okay. And yeah, go ahead, Nora.
No, that was a good summary. Yeah, and then just make sure that wherever you download it onto your computer, the most important thing, because this code won't run without that, is that you point this path here needs to point to where you put it on your computer.
Okay.
So if you download it and it goes into your downloads folder, this will probably, if it were on your computer, Cassie, it would be users Cassie downloads.
Okay. And then everything after it, and then you've got like the / data, and all of that, you want to have that in there.
And this would, for example, be downloads, and then put it into a file called data, and you'll find it from there.
Okay, that's good to know. And then everything else you can look up from both either the paper or from ExoFop, which is one of our favorites that we've gone to visit many, many times. And otherwise, just plug and play. It's a plug and play. Look at what Nora's already put together. Have a look through there. Is there maybe another tick ID example that you could put, not right now, but maybe just to give the citizen scientists an opportunity to go in and just try it on another tick ID as well?
Yeah, you can try my favorite tick ID, tick 555-25572. We'll do an episode where we go through the entirety of tick 555-25572 in a couple of weeks. So you can already play around with that and have a go, but we'll also show how we can get information from that one in a future episode.
Excellent. Awesome. Great summary, Nora. And like I said before, it's very good to see you. Was there anything else that you wanted to mention before we close out this episode for today?
No, it's great to see you. It's been so long. It's great to see everyone.
Good to see everyone. And I hope you forgive us for being off air for a while, but it was all for a good cause in the name of science. Nora getting her doctoral degree. I mean, that's kind of a big deal. Anyway, but yeah, okay. Well, thank you very much for joining us. And Nora, I guess I will see you next week. We're going to dive into astroseismology. I think that's what it's called. Starquakes. That's very exciting. I can't wait to talk about that. And then we will see you guys then. So see you next week. Good to see you, Nora.
Good to see you. Bye.
Bye.